Up to this point, I have covered all circuit analysis techniques and concepts using sources that do not change with time, and I call them DC or direct current sources. And now I'll shift my focus to sources that do actually change with time. Specifically, I'll start off with sources that are sinusoidal because they're easy to generate, they're easy to transmit, they're prevalent in nature. This is how we receive power to our homes. And also, they're arguably and relatively easier to handle mathematically. I'm saying arguably because we have to remember our trigonometry, but compared to sources that cannot be described by a mathematical function as simple as a cosine, for example, something like this, they're easier to handle mathematically. Okay, so in here, I'm showing you a voltage source, and that source actually changes with time in a sinusoidal format. So I'm going to take this source and I'm going to put it in a simple circuit in here to show you what we will do in this module. We have this circuit where the switch has been open for a very long time, and at time t equals 0, we close that switch, and what we get is just a single loop circuit with a resistor, an inductor, and a voltage source. And this time the voltage source, instead of being DC, it is actually just a sinusoid. So we'll try to solve this circuit, and it's simple. We just have to write KVL equation, and what we can do is we can say that this one here will be the V of R, and this one here would be the V of L. Okay, and we write the equation, and the equation is negative Vs of t plus V of R plus V of L equals 0. And in this particular case, we can focus on any of the V's, but what's interesting in this circuit is the I, because it is shared among all of them since it's a single loop. So we'll rewrite the V of R in terms of I and the V of L in terms of I. This is a source. We can't rewrite it in terms of I. We just substitute it eventually. So what we get is negative V of S t, while V of R, based on passive sign convention and Ohm's law, should be I of t times R plus, well, this is the voltage across an inductor, and we know that the relationship between the voltage and the current across an inductor is simply VL of t equals L of d I of t divided by d of t, and based on passive sign convention, in this particular case, we have the current hitting the positive, so what we do is we put positive in here, so that becomes L times di of t divided by d of t. And that equals 0. So we do a little bit of algebra in here, and what we end up with is di of t divided by d of t plus 1 over L divided by R I of t equals V of S divided by t, and this is multiplied by 1 of L divided by L because this is what we have. We divided everything by L, and of course we wrote it this way here just as a quick reminder. This is a first order circuit, so this is basically the tau, which is a time constant. And we substitute what the V of S is, which is simply this particular sinusoid, and what we end up with is di of t divided by d of t plus 1 over L divided by R I of t equals 1 divided by L times V of M, or we can just say this is V of M divided by L cosine of omega t. So this is a first order differential equation, and compared to the previous versions we've seen, in previous versions we've seen that this here is either 0 in a natural response of an RL circuit, or some sort of a V S equals 5 volts, or some sort of a constant for that matter. In this particular case, it's not a constant, it's also a function of time. So the solution here is a little bit more complicated than usual, so it will have a forcing function that is sinusoidal. The solution for this differential equation is a little bit more involved, and I will cover it in an optional video later. If you're interested in that, you can watch me just find the solution, but really the solution is of this shape. It looks this way. So the solution contains two parts. So let me just highlight these two parts in here. So the first part is, and I'll highlight it in this color in here. So this here is the first part, okay? And the second part is in here, which is in pink, okay? All right, so these are two parts. And these two parts, what I want you to pay attention to is the following. T appears in here, and this one here, T appears in here. That's where T appears. So as it turns out that this part in here has, well, the cosine, okay, the cosine of tan, blah, 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 whatever it is, this is not a function of time. It actually just is a single value. This is also not a function of time. So the whole thing in here is just can be computed if you plug in numbers to a scalar. And of course, L divided by R is a scalar. So what you end up with is e to the negative t something. So this here actually disappears with time. After 5 taus, it will disappear. And this is what we call a transient response, okay? A transient response because it actually disappears with time. It dies off. The signal dies off with time. On the other side in here, which is highlighted in pink, you'll see, well, yes, this is a scalar, but this is just a sinusoid. So this here actually is a function of time, and it will last as long as the switch is closed. And as it turns out to be, that we usually call this here is a steady state response. Okay? So it's steady state because as long as the switch is closed and the voltage source is not changing, it will basically be there. And that's how it is. So the current happened to be also a sinusoidal with the same frequency as the original source. Remember, the original source in here happened to be basically rotating at omega. This is the frequency for that. As it turns out to be that the current is also this way, but it has a different phase and it has a different amplitude in here, or magnitude. Okay, and the transient response in here actually lasts for a little bit, and then the steady state is actually just sinusoidal. So if you allow me, I'll jump a little bit ahead to show you what we'll cover in this module. Specifically, I'll tell you, well, you really do not have to solve this differential equation to get to a solution. There's actually ways around it. So I'm showing you this way without going into the details of how I get to it. So here's what I'll do. I'll show you that, and there are some things that you will not understand, but I just want you to get the general idea of what I'm doing. So what I'm doing is the following. We started off with what we call the time domain, because everything was a function of time, and we solved it like usual. It was I of t, Vs of t, we solved the differential equation, and we got that solution. And now what I will do is what we call a phasor transform. The phasor transform will change this circuit into this one here, and you'll end up with what we call a phasor domain. Okay, some people call it frequency domain. So in this phasor domain, what happens is it depends on the original forcing function. So the original forcing function that we got in here is the following. So this forcing function had the V of S had a magnitude that way and an omega. So here's what we do. Without going into the details, I'm going to tell you that this one here becomes not a function of time, but becomes V of M, which is a constant. That's why I'm using uppercases in here. Similarly, the current becomes, instead of function of time, it becomes I. Okay, we're going to deal with it as if it's a constant. We call it a phasor. But anyway, and R, actually, R, nothing happens to R. We keep it as R. L, what we do is we replace it with what we call J omega L. So let me explain what J is. J is simply the imaginary unit. If you remember in math, we said I squared is equal to -1. Now we use J squared because I for us is just current in here, as you can see it. So we say J squared. It's just simply the imaginary number unit. All right, what about omega? Well, omega comes from the cosine, from the original forcing function. Okay, and here's what we'll do. We will deal now with this circuit in here. We'll write KVL equation as if we are writing KVL equation for a DC source. But instead of dealing with the L as an inductor, I'm just going to assume that it's a resistor. It's actually technically called an impedance. And I'll just think that, well, instead of being R, I'm just going to basically use J omega L. So let me just explain. So I'm going to write KVL. Of course, that becomes negative V of M plus I times R. This is just simply Ohm's law. And now it's the same thing in here. We're going to apply Ohm's law, but now my R, or the resistance, or the impedance, is J omega L. And that equals 0. So that's what KVL tells me around that loop. So I'll do a little bit of change, I'll do a little bit of algebra just so that we can end up with I times R plus J omega L is just simply equals V of M. That means I, the thing I'm looking for, or almost I'm looking for I of t, but what I'm doing is I'm finding its equivalent in the phasor domain, divided by R plus J omega L. So hopefully you recognize that this one here is a complex number of the form A plus JB, and we can represent it in a different format if we wanted to. And that format, for example, is polar or exponential format. And in exponential format, this will be, the magnitude is A squared plus B squared under the square root, which is R squared plus omega squared L squared under the square root, e to the j omega, well, not omega actually, it will e to the j tangent minus 1, which is the phase of B divided by, well, A is R in our case. All right, so even if you don't remember complex numbers, I just want you to remember the following. We have some sort of a rectangular format. We're going to convert it to polar format. I'll cover exponential. I'll review not exponential, but complex numbers in a separate video for those of you that do not remember. But for now, I just will rewrite this original one into here. I is simply v of m divided by, it's the same number, but I just represent it in a different format. L squared, e to the j tangent minus 1 omega L divided by R. All right, so I'll just move this e to the other side in here, and what I will do is I'll end up with v of m divided by r squared plus omega squared L squared I e to the negative j tangent minus 1 omega L divided by R. All right, so now what I'll do is I'll do a little bit of magic, and I'll tell you we're going to do inverse phasor transform. Okay, so let me just explain. So what we have done is we started with the time domain, and then we went to a different domain in here. We called it a phasor domain, and we dealt with these elements the way we dealt with them. We wrote some sort of a KVL equation and ended up, this is the current in the phasor domain. So what I'll do now is I'll go back to the time domain, what we call an inverse phasor domain. I'll explain the detail later, but for now, what I want you to do is trust me by telling you, while I, uppercase I becomes I of t, equals, well, this is just a number, so we're going to keep it as is, r squared plus omega squared L squared, and this e to the j blah blah blah, this actually becomes cosine. It's utilizing Euler's equation, and we'll multiply by something called j omega t. For now, it doesn't matter. What matters is the following. It's omega t negative tangent minus 1 omega L divided by R. All right, and what I want you to do now is I want you to compare it to the following. So we got this solution in here. Let me just copy it and paste it down. Here it is. So hopefully you recognize that the solution we got in here, without having to deal with any differential equation whatsoever, is the same as the one here in pink. Look, the v of m divided by radical r squared plus omega squared L squared, this is it. And then the cosine in here is the same cosine in here. It's exactly the same. So what we were able to do is we were able to get the steady state response without having to deal with any differential equations, and very easily using just algebra. So frankly speaking, it's algebra with a little bit of complex numbers, so you have to remember complex numbers, but that's it. So the point of this module is the following. We will be able to solve circuits that are much more complicated than a single loop circuit that contains sinusoidal sources. We'll move to something we call a phasor domain, and in that phasor domain, we'll do a little bit of algebra, like normal circuit analysis techniques, and then we'll do what we call an inverse phasor. In an inverse phasor, we will be able to get the steady state response. However, the thing we will not be able to get is what we call the transient response. So by this process, by avoiding having to solve differential equations, we were able to get the steady state response, which one might argue it's more important than a transient response that disappears after a very short period of time, which is 5,000 here.